Hello and welcome to this clip on electron configurations and ionization energy. It's designed as either revision towards the end of your first or second year, or it could be your introduction to this topic for the first time. So assuming that you may be listening to this, watching this clip, because it's the first time you come across this idea, I'm going to include a comparison of the GCSE model of an atom as opposed to the orbital model as used as A-level and university and professional chemistry world. So first of all, I think it's important that you have a go at getting some of these definitions memorized, because I'll be making reference to them throughout the course of this clip, and it's often said that if you know your definitions, you're more than halfway there to understanding most of the questions that you'll come across. And if you don't know your definitions, you're most of the way there to not understanding any of the questions you come across. So in other words, definitions are extremely important to make sure you know them. So make sure you've learnt these off by heart if this is one of the first clips you're watching. Okay, so let's start with what you might have learned at GCSE. Right, so let's start where you would have been taught at GCSE. The model that you were taught at GCSE that's shown in the animation is the idea that electrons occupy simple shells around a nucleus. Now, there's nothing wrong with this model. It's actually quite feasible, and it does support many of the things that we have observed about atoms. It was put forward by a Danish chemist called Niels Bohr in the 1920s. Niels Bohr would have worked with people like Einstein and Heisenberg as well, if you've heard of those people, obviously. Now, the problem with this model is that there are variations in ionization energies between one element and the next that it doesn't explain. So when we have a situation where evidence is no longer supported by the model we're using, we have to come up with another model. This is where the A-level version, or what we call the atomic orbital model, comes in. So what actually happens is electrons sit in something called orbitals, and each orbital is a region that's around the nucleus where up to 2 electrons can be occupied. So if we were to look at the picture of the Bohr model, those 2 electrons would sit in an orbital. So an orbital could be represented by that, for example, or a p orbital could be represented by that, or an f orbital could be represented by that. And inside each orbital, you represent 2 electrons by arrows, showing that they spin in opposite directions. Now, there's a specific way in which orbitals are actually filled, because as you can see from the diagram at the bottom, in reality, what you've got is an axis. And this axis represents energy, or E for short. So the F electrons occupy orbitals and subshells with high energy, and the S electrons occupy orbitals with low energy. So as you increase or move away from the nucleus, you move towards the F electrons. So I'm just going to put here away from nucleus. So what we're going to look at next is how orbitals are actually filled, because it's a specific order in which they're filled. So if we look closely at this, we can see that in the bottom diagram, the way that the orbitals are filled follows the rules that are at the top of the page. So they fill in order of increasing energy. So, in other words, this is filled first. So this first shell, in each case, is filled initially, and then the second shell is filled. So this is the shell 1, and this is shell 2. So looking at the animation, you can see how the electron configurations start with 1s, then they move to 2s, then they move to 2p. So at the p side, you can see that what's happening this time is that the electrons tend to try and sit away from each other until they have no choice but to pair up. So at oxygen, for example, you can see that it's having to pair up at that point. So the animation shows it quite nicely, just moving through. So let's start with row 2 at the beginning. So for 2 electrons, helium, you have them in 1s2. Then 1s2, 2s1 for lithium, 1s2, 2s2 for beryllium, 1s2, 2s2, 2p1 for boron, 1s2, 2s2, 2p2 for carbon, 1s2, 2s2, 2p3 for nitrogen, and 1s2, 2s2, 2p4 for oxygen. So if you have a look at the total number of electrons, that will be represented by the configuration at the bottom of the animation, 1s2. So just setting the animation going again, you can see this time that the configuration takes a certain format, doesn't it? So the big number represents the shell number, the letter represents the kind of orbital, and the small superscript number represents the number of electrons. So if we were to look at an example, such as the ones at the bottom, we can say that boron, its configuration, has 2 plus 2 plus 1 equals 5 electrons in total. Carbon has 6 electrons in total. Nitrogen has 7 electrons in total, and oxygen has 8 electrons in total. So again, this should match up with what you've learned at GCSE, except what we're doing is we're representing the individual shells, and within those shells you have things called subshells. Within the subshells you have things called orbitals, or regions where up to 2 electrons can be found. So let's now look at the evidence for this model. Why do we use this model instead of the simple shells? I've mentioned ionization energy several times. Okay, so looking very quickly at ionization energy, which we defined earlier, there's a way you can write it out as an equation. So the equations at the top represent the first and second ionization energies of neon. And if you look at the graph at the bottom, you can see how the ionization energy is quite variable. So at the top of each of the, at the right-hand side of each of the periods, where you get the noble gases, they have the highest ionization energy. So all of these represent first ionization energies, and like I've just said, the noble gases have the highest ionization energy, but there's also a number of dips in ionization energy, such as at boron, oxygen, aluminium and sulfur, that can't be explained away by the simple Bohr model that you learned about at GCSE. So something else has to be going on here, and that's what we're going to look at next. So these are the relative first ionization energies in kilojoules per mole to the -1. Now, normally what you'd expect, just using the shell model, is that as you go across a period, such as from lithium across to neon, you'd expect there to be a nice solid sort of line increasing. And what that will be due to is increasing the number of protons, so therefore more attraction for the nuclei, more attraction for the outer electrons. However, what happens is you get dips. You get a dip at oxygen, and you get a dip at boron. You can also see dips at aluminium. So all of these have slight reasons why they're happening, but can only be explained by orbitals. So let's look at a couple of examples. So with aluminium, the 3p1 electron is shielded, so it's easier to remove. If we now look at another example, so with oxygen, the 3p4 electron, which is either one of these, 2p4 I meant to say, it experiences extra repulsion as it's forced to pair up, so it's easier to remove. So therefore this can allow us to explain some of these variations that we talked about earlier. So as you go across a period, you don't have any extra shells, so therefore there's no extra shielding, so the increase in ionization energy, the general trend we see, is due to greater nuclear attraction because you have more protons. However, you have dips in ionization energy, slight dips, as you go across a period, due to shielding from the P1 configuration in aluminium, for example, or P4 configuration due to repulsion. Now, although I said no shielding, or no extra shielding, but in the second point I'm talking about shielding, I'm talking about a very slight shielding. So in other words, we're still talking about the same shell. There's not an extra shell being added, just an extra subshell. But you can see that the numbers indicate you're still in shell 3. So the next thing to do is to talk about what actually causes, or what sort of things cause these changes, what are the trends, and what we need to talk about when we're doing exam questions. So when you're looking at exam questions that ask you to compare ionization energies of two elements, you can talk about atomic radius, because as it increases, the nuclear attraction decreases. So this is due to greater distance between the outer electrons and the nucleus. So if we have a small atom, and the nucleus in the middle, an electron in the outer shell, you have a small distance. With a big atom, nucleus in the middle, electron in the outer shell, bigger distance. So the next thing to talk about is the nuclear attraction, the proton number. So the basic idea is that anything that increases nuclear attraction means that there's now more energy needed to take outer electrons away, or to remove them. So ionization energy increases. So now we've looked at ionization, let's have a quick mention of chromium and copper, which are two unusual elements in the way that they fill their orbitals. So you can see there's an expected and an observed configuration for each of them, but looking closely, the observed configuration tries to maximize the amount of unpaired electrons that you've got. So what they do is they shift their electrons around a little bit. So what happens in chromium is one of the 4s electrons moves into an empty orbital in the 3D subshell, and what you get is a whole bunch of electrons that are now unpaired, and therefore less prone to repelling each other and less prone for the atom to be ionized. With copper, what happens is one of the 4s electrons goes in to join another electron in a 3D orbital, in a 3D subshell, and what that gives is a more stable configuration, because the paired electron is now in a lower energy subshell than it was before, so it's less likely to be lost to ionization. So looking at successive ionizations for one element, they can be used to work out when the how many shells it has, and also how many electrons there are in the outer shell. So in this one here, the outer shell is on the far right hand side, so you can see that it takes the most amount of energy. Sorry, that's the wrong way around, I'll just change that. That's better. Outer shell you start taking electrons from, and then you start on the third shell, then you start on the second shell, and then you start on the inner shell, like so. So because potassium has one electron in the outer shell, removing that takes a certain amount of energy, and then as you jump to another shell, you get an increase. So each of the jumps that I'm circling is due to a new shell having electrons taken away. Okay, so now it's time to try an exam question or two. So if you need to go away and read up on this first before we have a look, then please do so. Okay, so let's have a look at the different types of question they might ask you. The first type would be something to do with a graph they might present to you, and they might ask you to comment on the graph. So this would require you to have an understanding of how the first ionization energy changes across a period. So although you might not have space to do this on the exam paper specifically, as in space dedicated to it, it might be worth thinking about the electron configurations of each of the elements that you need to put the point in for, so then you can work out what might be the driving force behind that element's ionization energy. Would it be shielding? Would it be repulsion between electrons in the same orbital, for example? Or would it be proton number? So what I'm going to do is put the electron configurations of each of the elements down, and then we can have a go at adding them in. So what's quite handy about doing this is it also enables you to work out the proton number for each one. And proton number, as you know, could be one of the things that could affect ionization energy. Like that. So all I really did was I added up the number of electrons by looking at the numbers in superscript, and then that would tell me that there would be the same number of protons. So looking at the fact that sodium has 11 protons, magnesium is the next along in that particular part of the periodic table, so that magnesium is going to have 12 protons. So I would suggest that you could put sodium there. Now, moving from silicon to phosphorus, phosphorus will have 15 protons, silicon will have 14 protons, because it's the one before phosphorus in that row, but silicon will have 3p2. So if we look at 3p2, like so, and compare it to 3p3, which is phosphorus's configuration, then obviously what's going on here is that there's no difference in shielding. Because the same subshell is being filled. So here, its proton number is important. So if you look at silicon having 14 protons and phosphorus having 15 protons, then that must mean that the ionization energy, the first ionization energy for phosphorus, must be slightly bigger than that for silicon, and go there. So if we now think about what's happening with sulfur, sulfur has an interesting situation with its orbital filling, because if you look at its electron configuration, it's going to be p4. So you fill the orbitals like that, but now you have another electron, and that electron is undergoing repulsion. Now I want to draw them both in red. Oops, not like that. It's like this. Sorry, beg your pardon. Opposite spin. There we go. So that means these electrons these ones here are repelling one another, and therefore they're easier to remove. Therefore the ionization energy is lower. Okay, so what does that mean in terms of the likely placement of sulfur's ionization energy? Well, it would mean that because the electrons in the p subshell are repelling in one of the orbitals, that its value is going to be slightly lower, like that. So that allows us to join up the graph like so. So you're likely to get one mark here for sodium being lower than magnesium. You're likely to get a mark here for phosphorus being higher than silicon. And you're likely to get a mark here for saying that sulfur is lower than phosphorus. Okay, so what other type of example question could they give you? They could ask you about successive ionization energy data and ask you to predict what you think the likely number of outer electrons it has in its outer shell. So let's look at an example of that. So what we have to do here is think about what's going on at this point. And like we've said before, this means that there is a movement from an outer shell to an inner shell. So these two would be outer shell electrons. And these three would be inner shell electrons, as in the next shell down. So the big jump in ionization energy means there must be 2 electrons in the outer shell. So the only the only period 3 element that has 2 electrons in its outer shell is magnesium. So we can put down the element is magnesium because a large jump or large increase in ionization energy from 2nd to 3rd ionization energy, meaning 2 electrons outer shell. Okay, there's one more type of ionization energy exam question they might ask you about, and that's a simple worded explanation. So I'm going to move to a new slide here to have a look at this. So this is the 3rd type of exam question you can come across, where they ask you to descriptively explain a difference between ionization energies of elements. So it might be the first ionization energy of 2 elements, or it might be the second ionization energy of 2 elements. So it's worth thinking again about the things you need to consider when you're talking about ionization energy. So if you look at this diagram, just to remind ourselves, you can see that as you go down a group, any group, the number of shells increases, so therefore the shielding and the atomic radius increases, and the first ionization energy increases. So if we remember what the second ionization energy actually is, we can now apply this to the 2 elements we're being asked to compare. So Mg plus goes to Mg2 plus, and the same thing happens with strontium. what we've got to think about is what might cause this value to be higher for magnesium. So if we look at where magnesium sits compared to strontium, in the periodic table in group 2, if we just sketch it out like this, with beryllium at the top, then magnesium, then calcium, then strontium, then barium. And if we highlight the two that we're looking at, we can now reach a conclusion. And the conclusion is, first of all, ionic radius in Mg smaller. We can also say Mg plus electrons experience less shielding. And we can also say that therefore nuclear traction in Mg plus is greater than in Sr plus. Obviously you can say the reverse, you can say ionic radius in Sr is smaller, so the or reverse argument is fine. Okay, now I think that pretty much covers us for the types of exam questions you might come across. There's lots of different variations on those basic themes. So just to recap, they would give you data and ask you to make comment on it, or they would give you a graph and ask you to either make comment on it or complete it, or they'd ask you to compare two elements, in which case you'd have to use the periodic table and your knowledge of what happens as we go down a group. The diagram on the screen giving you some idea of what to talk about. So, just so you're aware as well, when you're talking about ionization energy, you always talk about the number of shells, the shielding, atomic radius, and that should cover you. The only other thing that you might want to consider as well is nuclear charge or proton number. Okay, thanks for sticking with this clip. It's a slightly longer one than normal, but there is more things to cover. I hope you found it of some use, and in particular, you can go away and use it to try out some past paper questions now. As always, take any queries you've got to your teacher in the first instance, or perhaps for subject extension. But thanks again for sticking with it, and appreciate you listening. Bye.